So this is the describing and measuring motion homework. Like always, let's take a look at the reading preview, key concepts and key terms. So the key things to keep in mind, the key concepts are: when is an object in motion? How do you know an object's speed and velocity? And how can you graph motion? And then some key terms are things like motion, obviously, reference point, the International System of Units, although I wouldn't worry too much about that. It's still good to know what an ISU is. Meter, speed, average speed, instantaneous speed, velocity, and slope. Let's start reading. How do you know if you are moving? If you've ever traveled on a train, you know you cannot always tell if you are in motion. Looking at a building outside the window helps you decide. Although the building seems to move past the train, it's you and the train that are moving. However, sometimes you may see another train that appears to be moving. Is the other train really moving, or is your train moving? How do you tell? Describing motion. Deciding if an object is moving isn't as easy as you might think. For example, you are probably sitting in a chair as you read this book. Or watch this video, I should say. Are you moving? Well, parts of you may be. Your eyes blink and your chest moves up and down, but you would probably say that you are not moving. An object is in motion if its distance from another object is changing. Because your distance from your chair is not changing, you could say you are not in motion. Reference points. To decide if you are moving, you use your chair as a reference point. A reference point is a place or object used for comparison to determine if something is in motion. An object is in motion if it changes position relative to a reference point. Objects that we call stationary, such as a tree, a sign, or a building, make good reference points. From the point of view of the train passenger in Figure 1, such objects are not in motion. If the passenger is moving relative to a tree, he can conclude that the train is in motion, and not the tree. You probably know what happens if your reference point is moving. Have you ever been in a school bus parked next to another bus? Suddenly, you think your bus is moving backward, but then you look out a window on the other side, you find your bus isn't moving at all. The other bus is moving forward. Your bus seems to be moving backward because you use the other bus as a reference point. Relative motion. Are you moving as you read this book or watch this video? The answer to that question depends on your reference point. When your chair is your reference point, you are not moving. But if you choose another reference point, you may be moving. Suppose you choose the sun as a reference point instead of your chair. If you compare yourself to the sun, you are moving quite rapidly. This is because you and your chair are on Earth, which moves around the sun. Earth moves about 30 kilometers every second. So you, your chair, this book, this video, everything else on Earth move that quickly as well. Going that fast, you could travel from New York City to Los Angeles in about 2 minutes. Relative to the sun, both you and your chair are in motion. But because you are moving with Earth, you do not seem to be moving. You can't tell that you're moving. So let's take a look at this figure here. So relative motion from the plane. The plane does not appear to be moving. Skydivers appear to be moving away. A point on the ground appears to be moving away. To the skydiver, the plane appears to be moving away. The skydivers do not appear to be moving. The ground appears to be moving closer. And compared to the ground, the relative motion from the ground, the plane appears to be moving across the sky. The skydivers appear to be moving closer, and the ground does not appear to be moving at all. So you have to be careful choosing your reference points to figure out what's really moving and what's not. All right, here we go. Calculating speed. A measurement of distance can tell you how far an object travels. A cyclist, for example, might travel 30 kilometers. An ant might travel 2 centimeters. If you know the distance an object travels in a certain amount of time, you can calculate the speed of the object. Speed is a type of rate. A rate tells you the amount of something that occurs or changes in 1 unit of time. The speed of an object is the distance the object travels per unit of time. How far something goes in a certain amount of time. That's speed. To calculate the speed of an object, divide the distance the object travels by the amount of time it takes to travel that distance. This relationship can be written as an equation. Speed equals distance divided by time. The speed equation consists of a unit of distance divided by a unit of time. If you measure distance in meters and time in seconds, then you express speed in meters per second, or m/s. The slash is always read as per. You could also read it as divided by if you're thinking mathematically, right? Meters divided by seconds, distance divided by time, right? Meters is distance, seconds is time. But we would never say that if we were speaking, oh, we're going 84 miles divided by hours. That wouldn't make sense, right? Oh, we're going 84 miles per hour. That's how we would say it. Although that would be fast. Don't do that. That would be speeding. If you measure distance in kilometers and time in hours, you express speed in kilometers per hour, or km/h. For example, a cyclist who travels 30 kilometers in 1 hour has a speed of 30 kilometers per hour. And an ant that moves 2 centimeters in 1 second is moving at a speed of 2 centimeters per second. There are some cyclists riding their bikes through what looks like a sunflower field. Looks awesome. Average speed. The speed of most moving objects is not constant. The cyclists shown in Figure 4, for example, change their speeds many times during the race. They might ride at a constant speed along flat ground, but move more slowly as they climb hills. Then they might move more quickly as they come down hills. Occasionally, they may stop to fix their bikes. Although a cyclist does not have a constant speed, the cyclist does have an average speed throughout the race. To calculate average speed, divide the total distance traveled by the total time. For example, suppose the cyclist travels 32 kilometers during the first 2 hours. Then the cyclist travels 13 kilometers during the next hour. The average speed of the cyclist is the total distance divided by the total time. So you would add up those distances, 32 kilometers and 13 kilometers, which is 45. The total time, which is 3 hours, and then you would divide 45 by 3 to get 15 kilometers an hour. The cyclist's average speed is 15 kilometers per hour. Calculating the average speed of a cyclist during a race is important. However, it is also useful to know the cyclist's instantaneous speed. Instantaneous speed is the rate at which an object is moving at a given instant in time. Describing velocity. Knowing the speed at which something travels does not tell you everything about its motion. To describe an object's motion completely, you need to know the direction of its motion. For example, suppose you hear that a thunderstorm is traveling at a speed of 25 kilometers an hour. Should you prepare for the storm? That depends on the direction of the storm's motion. Because storms usually travel from west to east in the United States, you need not worry if you live to the west of the storm. But if you live to the east of the storm, take cover. When you know both the speed and direction of an object's motion, you know, oh my gosh, excuse me, I yawned right in the middle of the sentence. When you know both the speed and direction of an object's motion, you know the velocity of the object. Speed in a given direction is called velocity. Speed and direction is what velocity is. You know the velocity of the storm when you know that it is moving 25 kilometers per hour eastward. This is kind of funny, the tech and design in history. Horse-drawn wagon. Funny bicycle. Tricycle, actually. Old car. All these things can have speeds, I guess. At times, describing the velocity of moving objects can be very important. For example, air traffic controllers must keep close track of the velocities of the aircraft under their control. These velocities continually change as airplanes move overhead and on the runways. An error in determining a velocity, either in speed or in direction, could lead to a collision. Velocity is also important to airplane pilots. For example, stunt pilots make particular use of their control over the velocity of their aircrafts. To avoid colliding with another aircraft, these skilled pilots must have precise control of both their speed and direction. Stunt pilots use this control to stay in close formation while flying graceful maneuvers at high speed. Graphing motion. So take a look here at this graph for a second. Distance versus time graphs are always showing you speed. So if there's a distance and a time, time is almost always on the x-axis, distance is almost always on the y-axis. This is showing you speed, and so this object was going at a constant speed, constant rate, because its line was straight. All right, graphing motion. You can show the motion of an object on a line graph in which you plot the distance versus time. The graphs you see in Figure 6, what we just looked at, are distance versus time motion graphs. Time is shown on the horizontal axis or the x-axis. Distance is shown on the vertical axis or the y-axis. A point on the line represents the distance an object has traveled at a particular time. The x value of the point is time and the y value is distance. The steepness of a line on the graph is called slope. The slope tells you how fast one variable changes in relation to the other variable in the graph. In other words, slope tells you the rate of change. Since speed is the rate that distance changes in relation to time, the slope of a distance versus time graph represents speed. The steeper the slope is, the greater the speed. So the steeper the line is on the graph, the greater the speed. A constant slope represents motion at a constant speed. So if it's a straight line, that means it's going at a constant speed. Straight meaning it's not bending. Calculating slope. You can calculate the slope of a line by dividing the rise by the run. The rise is the vertical difference between any 2 points on the line. The run is the horizontal difference between the same 2 points. In Figure 6, using the points shown, the rise is 400 meters and the run is 2 minutes. To find the slope, you divide 400 meters by 2 minutes. The slope is 200 meters per minute. Let's look at that. So it's saying in 2 minutes, or I should go this way, right? Rise is 400 meters and the run is 2 minutes. So 400 divided by 2. 200 meters per minute. So if you wanted to find that point, you could say, okay, it's going 400 meters for every 2 minutes. That means it's going 200 meters for every 1 minute. Different slopes. Most moving objects do not travel at a constant speed. The graph above shows a jogger's motion on her second day. The line is divided into 3 segments. The slope of each segment is different. From the steepness of the slopes, you can tell that the jogger ran the fastest during the 3rd segment. The horizontal line in the 2nd segment shows the jogger's distance did not change at all. It means that they stopped. All right, next section, acceleration. Key concepts. What kind of motion does acceleration refer to? How is acceleration calculated? And what graphs can be used to analyze the motion of an accelerating object? Key term, acceleration. The pitcher throws. The ball speeds towards the batter. Off the bat it goes. It's going, gone! A home run. Before landing, the ball went through several changes in motion. I'm sorry, I can't even handle myself. That was ridiculous. I'm sorry. Before landing, the ball went through several changes in motion. It sped up in the pitcher's hand and lost speed as it traveled toward the batter. The ball stopped when it hit the bat, changed direction, sped up again, and eventually slowed down. Okay, so just imagine a ball hitting a bat, the bat hitting it forward, right? There's lots of changes in speed and direction happening there. Most examples of motion involve similar changes. In fact, rarely does any object's motion stay the same for very long. What is acceleration? Suppose you are a passenger in a car stopped at a red light. When the light changes to green, the driver steps on the accelerator. As a result, the car speeds up or accelerates. In everyday language, acceleration means the process of speeding up. Acceleration has a more precise definition in science. Scientists define acceleration as the rate at which velocity changes. Recall that velocity describes both the speed and direction of an object. A change in velocity, so either speed or direction, can involve a change in either... I just said that. I need to just read it. A change in velocity can involve a change in either speed or direction or both. In science, acceleration refers to increasing speed, decreasing speed, or changing direction. Remember, main ideas are usually bolded, so this is the key term, this is the main idea. Increasing speed. Whenever an object's speed increases, the object accelerates. A softball accelerates when the pitcher throws it, and again when a bat hits it. A car that begins to move from a stop position or speeds up to pass another car is accelerating. People can accelerate too. For example, you accelerate when you coast down a hill on your bike. Decreasing speed. Just as objects can speed up, they can also slow down. This change in speed is sometimes called deceleration or negative acceleration. For example, a softball decelerates when it lands in a fielder's mitt. A car decelerates when it stops at a red light. A water skier decelerates when the boat stops pulling. Even an object that is traveling at a constant speed can be accelerating. Recall that acceleration can be a change in direction as well as a change in speed. Therefore, a car accelerates as it follows a gentle curve in the road or a change in lane. Runners accelerate as they round the curve in a track. A softball accelerates when it changes direction as it is hit. Many objects continuously change direction without changing speed. The simplest example of this type of motion is circular motion, or motion along a circular path. For example, the seats on a Ferris wheel accelerate because they move in a circle, so they're constantly changing direction. Calculating acceleration. Acceleration describes the rate at which velocity changes. If an object is not changing direction, you can describe its acceleration as the rate at which speed changes. To determine the acceleration of an object moving in a straight line, you must calculate the change in speed per unit of time. This is summarized by the following formula: final speed minus initial speed divided by time. If speed is measured in meters per second and time is measured in seconds, the SI unit of acceleration is meters per second, or meters per second squared. Suppose speed is measured in kilometers per hour and time is measured in hours. Then the unit for acceleration is kilometers per hour, or kilometers per hour squared. To understand acceleration, imagine a small airplane moving down a runway. Figure 10 shows the airplane's motion after each of the first 5 seconds of its acceleration. To calculate the average acceleration of the airplane, you must first subtract the initial speed of 0 meters per second from the final speed of 40 meters per second. Then divide the change in speed by the time, 5 seconds. So its acceleration would be 8 meters per second squared. 40 minus 0 is 40, divided by 5 seconds, 8 meters per second squared. Of course, this doesn't include a change in direction because it's just going straight, but it should eventually, let's see at the drawing. So it's not considering the point at which the plane starts to lift off the ground yet. The airplane accelerates at a rate of 8 meters per second. This means that the airplane's speed increases by 8 meters per second every second. Does that make sense? So every second, the speed of the airplane is increasing by 8 meters per second, and that's what acceleration is. Notice in figure 10 that after each second of travel, the airplane's speed is 8 meters per second greater than it was the previous second. Oh, you can barely read it. It's down here. 8 meters per second, 16 meters per second, 24 meters per second. All right. This is just some math practice. Speed versus time. So this would be a graph showing acceleration. Speed over time will actually show you acceleration. So, graphing acceleration. Suppose you ride your bicycle down a long steep hill. At the top of the hill, your speed is 0 meters per second. As you start down the hill, your speed increases. Each second you move at a greater speed and travel a greater distance than the second before. During the 5 seconds it takes you to reach the bottom of the hill, you are an accelerating object. You can use both a speed versus time graph and a distance versus time graph to analyze the motion of an accelerating object. Figure 11 shows you a speed versus time graph for your bicycle ride down the hill. Speed versus time. Slope is 2 meters every 1 second. 2 meters per second every 1 second, I should say. Oh, I just messed that up, right? 2 meters per second every 1 second. It's increasing. So that's showing you the acceleration is 2 meters per second squared. Stuff is tricky. All right, what can you learn about the motion? We just did that. First, since the line slants upward, the graph shows you that your speed was increasing. Next, since the line is straight, you can tell that your acceleration was constant. A slanted straight line on a speed versus time graph means that the object is accelerating at a constant rate. You can find your acceleration by calculating the slope of the line. We just did that. To calculate the slope, choose any 2 points on the line, then divide the rise by the run. During your bike ride, you accelerated down the hill at a constant rate of 2 meters per second squared. Distance versus time graph. You can represent the motion of an accelerating object with a distance versus time graph. Figure 12 shows a distance versus time graph for your bike ride. On this type of a graph, a curved line means that the object is accelerating. The curved line in Figure 12 tells you that during each second you traveled a greater distance than the second before. For example, you traveled a greater distance during the 3rd second than you did during the 1st second. The curved line in Figure 12 also tells you that during each second your speed is greater than the second before. Recall that the slope of a distance versus time graph is the speed of an object. From second to second, the slope of the line in Figure 12 gets steeper and steeper. See, it's getting steeper. Since the slope is increasing, you can conclude that the speed is also increasing. You are accelerating. All right, last bit here, sailing through the solar system. Scientists and engineers are always looking for ways to improve things. They try to achieve 2 goals, making things work better and making them cost less. The more complex a project, the bigger the challenge. From this perspective, one of the biggest challenges is space travel. A great deal of energy is required to send spacecraft into space. Powerful rockets are needed to launch spacecraft and to provide the velocity they need to travel through the solar system. These rockets are expensive. Oh, see, they just used the word velocity as speed. That bugs me. We know that velocity is speed and direction, so it would have been better if they said to provide the speed they need to travel through the solar system. Anyway, these rockets are expensive. The fuel is expensive too. How could space travel be made less expensive? One idea that scientists are exploring is solar power. Some scientists believe that a spacecraft could actually sail through the solar system. Solar sailing spacecraft could travel large distances through the solar system using very little fuel. Sailing boats on Earth. On Earth, sailboats glide across lakes, oceans, and bays. Sailboats need no fuel. They are powered by the wind. When the force of the wind is greater than the drag, or friction, of a sailboat on the water, the wind pushes the boat forward. The navigator speeds the boat up or slows it down by controlling the angle the sails make with the wind. The navigator can also use the force of the wind and the rudder to change the direction the boat is going. But in space, there is neither air nor wind. So how could a spacecraft sail? The answer is this. Spacecraft may be able to sail using the pressure of sunlight. How solar sails would work. Sunlight is made of tiny energy packets called photons. If light traveling in straight lines out from the sun struck the sails of a spacecraft, the photons would bombard the sail like tiny ping pong balls. When the photons struck the sail, they would push on it with very small force. Because there is no air friction in space, the spacecraft would sail along with only the pressure of the photons of light and gravity acting on it. So far, so good, but here's the drawback. A very large force is needed to accelerate something as big as a spacecraft. Photons come in vast quantities, that means a lot, big groups, but their individual power is small. One way to increase the force would be to make the sails of the spacecraft larger. In this way, more photons would hit it. But scientists have estimated that to catch enough photons to make a spacecraft move, the sails would have to measure a kilometer on each side. A sail that big would cover about 175 football fields. More solutions. Another way to maximize the force of the photons on the sails would be to make sure the light reflects off the surface of the sails as strongly as possible. This could be accomplished by manufacturing sails from material that reflects light like a mirror. Another solution might be to make the sails as lightweight as possible. Scientists and engineers will be challenged to develop and design sails made of ultra-lightweight materials, so the spacecraft will have as little mass as possible. Scientists and engineers are creative. They have many ideas about how to make space sailing work, but they do agree on one thing. Designing huge sails that have very little mass and that are highly reflective is a real technological challenge. There are no solar sailing spacecraft yet, but scientists do hope to have them one day. These spacecraft could be placed in positions that would allow them to constantly monitor Earth and the Sun. The findings they would transmit could help us better understand weather patterns and climate changes on Earth, as well as storms on the Sun. Solar sailing spacecraft might be able to visit planets, moons, comets, and asteroids and send back exciting new data. Some scientists even hope to use such vehicles someday to send a spacecraft to the stars. Solar sailing is a dream of the future, but scientists and engineers are working to make it happen. New materials and technologies will be needed, new challenges will be met, and new discoveries made. All right. That's all. Hope this was helpful.